take a look at this question. So whenever they tell you to use nodal analysis, the first thing that you need to do is you need to identify where your nodes are. So let's look at node A over here first. So node A is over here, but actually there's no difference between node A and the node next to it. Let me just show you. So I'm going to get this fill. I'm going to put this in there. So I need to change the type of fill, color. There we go. Okay. So node A is over here, but the thing is it's connected to this other node over here. And that's actually the same node because there's nothing in between it. There's no resistor here, there's no capacitor, there's nothing here between them. So the voltage between these two sections is actually exactly the same, which means that they're the exact same node. So we're going to do that. So we've made A bigger node here. It's like a gigantic node now. And we can do the exact same thing over here. So this over here, this section doesn't have any devices in it. So it's actually the same node. And we can continue on over here. So that's actually also part of this A node. Okay, that looks like it's about done. We can move over to the B node now. So B node starts over here, but but it can go down here because there's no device there. Oops. So let's move that over a little bit. We can also extend the B node up to here and up to here because there's no devices. And we can extend it over here. And we can extend that down here. And that's pretty much it. All these other lines over here have something in them. Actually, while we're here, we can take a look at this resistor over here. You can see that electricity moving into this B node over here can take two paths. It can, here, let me make this a little bit thicker. So it can go, so like let's say it's coming up from here. It can take two paths. So the 6 ohm resistor over here is in parallel with this wire over here. So you can take the wire path, the electricity can go this way, or it can go this way. And since there's nothing on this path over here, it means that the electricity is going to take this way because there's no resistance. It's not going to follow this path at all. So this path might as well not exist. There's no electrons that are going to travel down that way. So we can get rid of this resistor. Sorry, one sec. Let's go ahead and get rid of that. Like that. Yeah, so that's it for node B. You can see over here there's a resistor, there's a resistor, current source, and there's a resistor over here, which, yeah, okay. Okay, let's check out node C over here. So we'll draw that out. So node C starts here. And there's nowhere it can really extend to. So that's basically it. That is node C right there. And there's one more node that is labeled here. It's labeled O, or it could be labeled 0. I think the idea behind labeling it 0 is to say that it's the ground. But it could be labeled anything. It could be like F or G or whatever. It doesn't matter. For our purposes, we're going to call that the ground. And I'll tell you why in a second. But for now, let's extend it. So, oops. And actually, let's give it a purple color. Okay. So the ground, it extends out to this node over there. It also extends up into this node. Technically, you could extend it here as well if you wanted. It doesn't really make a difference because the idea is that the electricity is coming to this part over here. And we'll talk a little bit about how I know the electricity is going that way or not. first we're going to extend this node. This will go up as well, up to here, and then it'll also go up to here, and then we'll keep on going to here, and to here, and to here, and to here. It's a gigantic node, and we're going to call it the ground node because, well, there's two reasons for that. The first reason is that usually on these electrical schematics, the bottom row is the ground node. And the second thing is we can actually define the ground node to be wherever we want it to be. The reason why is because voltages are always relative. This is kind of a complicated thing, so you might want to just take my word for it, but I'll give you a quick explanation here for anyone that's interested. So the idea is that voltage is relative, right? So voltage is kind of like energy. It's not quite, but it's almost like energy. And energy is also relative. Just to give you an example, let's say, for example, you're on top of, let's say you live in Tibet. So technically you live on top of this big hill. You know, Tibet is a mountainous area. So you're doing an experiment to see, you know, the gravitational potential energy of a ball that you throw up. So you throw it up, it comes down. When it hits the ground, you would say the energy is 0, right? And when you're up here, you'd say like, oh, well, it went up 10 meters, so the energy is like 100 joules or something like that. So that's relative to you, relative to your ground position, right? The ground, the place where the energy is 0. Get it? Ground. Okay. But someone who's down here, maybe in mainland China, he doesn't consider your ground to be his ground. Technically, that ball that you've thrown up that's hitting the ground for you actually has a height that's quite high. Let's say it's, I don't know, 100 meters or something like that. So its energy is actually going to be quite high. It's going to be, I don't know, maybe 1,000 joules or something like that. So it's, the point I'm trying to make is that it's all relative, and you can define your ground to be anywhere you want. You're going to get the same answer either way. Well, you're going to get the same relative answers. Technically, you're going to get the correct answer, but it just might be different, kind of like how you define energy in that ball scenario. But rest assured, the point I'm trying to make is that your teacher is not going to give you less marks if you set your ground somewhere else. But this is a good place to set the ground because it's at the bottom of the schematic. Like I said, that's usually where the ground is. And also it's a gigantic node, which means there's going to be a lot of stuff coming into it. And you'll see why it's actually a good idea to list the largest node as your ground. Okay. So I'll show you why. So so why have a big ground node. Okay, so we'll answer this question by first figuring out the equation for the currents in node A. Okay, so for node A, we're going to arbitrarily assign the currents going in and out. This is fine. Later on, we'll see if our assumptions are incorrect or not, but it doesn't change the answer. I know it's a lot of confusing this stuff to throw at you right away, but just trust the process at this point. Okay, so we're going to say the current is going up from the ground into A over here. And I'm just going to say that the current is leaving the node here and here. We'll say the current is leaving here and the current is leaving here. Okay. So with that, we'll write our Kirchhoff current law over here. So we know that the current coming into the node has to equal the current that's leaving the node. And that's just reasonable, right? Like if 100 people show up to your party, 100 people have to leave your party, right? So let's take a look at what's coming in. So what's coming in is 1 milliamp over here. So we're going to have that 1 milliamp. And over here, we see that there's this current leaving over here. So that current, what's its value going to be? Well, let's look at Ohm's law. So this says that the voltage drop across a resistor is equal to the current moving through the resistor multiplied by the resistance of that resistor. And the current moving through this resistor is going to equal the current leaving this node at this particular area, right? Because whatever current exits here has to go through this resistor. So the current moving through that resistor is going to equal the voltage drop across that resistor over the resistance of the resistor. And the voltage drop across that resistor is just the difference in voltage from this point here to this point here. And you can actually extend those a little bit. You could say it's the voltage difference between this point here and this point here. And the reason why you can do that is because there's nothing going on in these wires. There's no voltage drop. So the voltage that's here is equal to the voltage that's here. Okay, so the voltage that's here, we're going to define that as VA. And the voltage that's down here is 0 because it's ground. So it's just going to be minus 0 over the resistance, which is 2 kilo ohms. Okay. So hopefully that makes sense. It's the voltage drop, like if you imagine you have a situation like this. If the voltage at this point A is 10 volts and the voltage here is 0, then you know that 10 volts dropped across that resistor. If you had a situation where you had 10 volts and you had 5 volts here, well, you know that 5 volts must have dropped, right? It would have been 10 minus 5. So that's the voltage drop, and that's the resistance. So get rid of that. Okay, so that's the current. This equation here represents the current that's moving through here. Okay. And sorry, this is a little confusing. I should have put an equal sign here. Okay, so the voltage drop is equal to VA minus 0, and the resistance equal to 2 kilo ohms. Okay, so all right, so when we're listing all the currents moving out, the first current that's moving out is going to equal VA over 2 kilo ohms. Then there's another current over here, and we use the same logic. In this case over here, we're moving from node A to node C, and there's a current. This current has a voltage drop associated with it due to the resistor. So the current moving through this 1 kilo ohm resistor is equal to the voltage drop across the resistor over the resistance. And the voltage drop is the difference between VA and VC. That's over resistance. You might be wondering why it's not VC minus VA, by the way. Why is it not this? The reason why is because you always start with the larger voltage. And you know that VA has a larger voltage than VC because the current is running from A to C, right? Electricity always runs from high voltage to low voltage. Just like how things move from high energy to low energy, right? Like you throw a ball in the air, then it has a lot of gravitational potential energy, and it moves to the position where it has 0 gravitational potential energy, which would be the ground. Okay, so in this case, the current moving through this 1 kilo ohm resistor is current is equal to the drop in voltage over the resistance. That would be VA minus VC, and then that would be over 1 kilo ohm. Okay, so that's the second one. So we'll add that up here because it's the sum of the voltages out. Sum means you add. So that's VA minus VC over 1 kilo ohm. Okay. Then we have these two currents over here. So we have this one over here, which we know is 3 milliamps because the current source tells us that. So that's going to be plus 3 milliamps. And then this one over here is a little bit more interesting because it has to go from node A, then it has to go through a battery, but it's going through the opposite direction of a battery. That's important because if you're going through a battery, right? Like let's say you have a battery like this and you're going through it the right way from the negative side to the positive side, then you gain energy, right? That's what a battery does. It's kind of like in Mario Kart, those little stripy lines give you a lot of speed to go. If you go against those stripy lines, right, it takes energy. So if you go through the wrong end of the battery, you have to lose energy to push your way through it. And the amount of energy that you lose, or the amount of voltage that you lose, is actually equal to the voltage of the battery. So 4 volts in this case, because that's what the battery voltage is. And then you have to go through this 1 kilo ohm resistor, and then you end up at node B. So this current that's moving through here, well, is equal to the current that's moving through the resistor. And the current that's moving through the resistor is same deal. V drop over the resistance. And it's a little bit more interesting because it's going to be VA, right? The voltage drop is going to be, just to kind of illustrate this actually. Let's say that A is 10 volts and B is 0 volts. Well, if you're an electron and you're moving through this battery, first of all, you're going to lose 4 volts. So you're going to be at 6 volts. And then when you go through this resistor, you're gonna lose 6 volts because this is 0 over here. Let me give a better example actually. So let's say you're at this position here, A, and that's 10 volts. Then you go through a battery the wrong way, and then you go through a resistor and you head to this position B, which is equal to 1 volt. And if the battery's voltage is 4, then you lose 4 volts going across it or through it. So you have 6 volts left over, right? So the voltage here is 6, and the voltage down here is 1, which means that when the current moves through this resistor, it drops 5 volts, right? So now the electron just has 1 volt. It gets to the bottom. So what we need to do is we need to say, okay, VA, to figure out how much of a voltage drop there is across the resistor, what we do is we say, here, let's clean this up a little bit. So we would say, okay, you start off, it's your starting voltage. And this is your ending voltage. So your starting voltage, you subtract the voltage of the battery, which in our case is 4 volts. And then you subtract the ending voltage, which in this case is VB, because the current is going to go through here and go to this B node. And what you have left over is going to be the voltage drop across the resistor, right? So in this case, it would be 10 minus 4 minus 1, and that would be 5, right? So the battery, the electron goes through the battery, loses 4 volts, it's got 6 volts left, and it has to drop 5 volts here so that it has 1 volt down here. 5, right? So yeah, to simplify it, just make sure you subtract the battery if you're going the wrong direction. If you're going the right direction, you add the battery. Okay, so that's that, and the resistance that's going to go through is 1 kilo ohm, so we'll just write that down. Okay, so that's the equation there. Okay, so almost there. We're going to have VA minus 4 volts minus VB over 1 kilo ohm. Okay. Do we have any other things here? So we accounted for this one, we accounted for this one, yes, we counted for that, we counted for this, so I think we're good. So 1, 2, 3, 4, it's always good to count. So here's one current coming in, and we have one equation, 1 milliamp. We have 1, 2, 3, 4 currents leaving, and we have 4 terms here, so we're good. Okay, so a lot of people like to just leave it like this, but I like to simplify the equation a little bit more, just to make it easier for ourselves. And the good way to do this is just to multiply everything by the common denominator here, the largest common denominator. So if I multiply by 2 kilo ohms, what we're going to have is 2 kilo ohms multiplied by 1 milliamp is equal to VA, because the 2 kilo ohms cancel out when you multiply the side. Then you're going to have 2 times VA minus VC plus 2 kilo ohms multiplied by 3 milliamps plus 2 times VA minus 4 volts minus VB. Doesn't look simple yet, but we'll get there. So 2 kilo ohms times 1 milliamp, that's just 2 volts. That's going to equal VA plus 2 VA minus 2 VC plus 6 volts plus 2 VA minus 8 volts minus 2 VB. Let's move all the voltages to the other side. So that's going to be this and this are going to come together to make -2. When you move -2 to the other side, you get 4 volts. Then you have the VAs, so that's got to be VA. So VA, that's 1, 2, 3, 4, 5. Is that right? 1, 2, 3, 4, 5. Okay, so it's 5 VA. And then we do the VBs and VCs. So that's -2 VC. And what about, are there any? Yeah, okay, so that's 2 VB. All right. So yeah, that's a little bit easier, isn't it? A little bit simpler of an equation. So let's move that over here. And we'll get rid of all this other stuff. So that's the equation for node A. Okay, so let's label that. We'll just say equation 1. It doesn't really matter that you say it's node A. You'll see why in a bit. So you can see why, actually now let's answer our question. Why is it good to have a big node, big ground node? The reason why it's important to have a big ground node is because it simplifies your calculations a lot. Like for example, this current over here, this one, remember it was current is equal to VA minus 0 over 2 kilo ohms. And the reason why it's -0 is because this is ground, right? So if you have a lot of things plugging into the ground, then your equations will become easier because you can just write 0. So that's why you should make a big ground. Hopefully that makes sense. Okay, so let's get rid of that. Next, we're going to do node C, let's say. Node C looks easy, so we'll do node C. So node C, we have this current coming out of node A going into node C. So we'll keep that going. We need to make sure we're consistent. Here we can just decide which direction we want. I'll say it goes that way, and this one I'll say it goes that way. Okay. So for node C, there's only one current coming in and 2 currents coming out. So the current that's coming in is going to be the voltage at A minus the voltage at C over 1 kilo ohm. And it's just a reminder, this is the current that's moving through this resistor. So that's the potential difference is VA minus VC, and then divide by the resistor will give you the current. Okay, and the current going in has to equal the current going out. So this one over here, it's going to go from C, so VC, and it's going into the ground, right? So that's really nice. It's just minus 0 is equal, and then 2 kilo ohms at the bottom. And we're adding, because it's summation. Remember, summation of currents out. This current over here is going to be VC minus 0, again, because it's going to ground. And that's also going to be over 2 kilo ohms. And now we're going to scroll down if I can manage it. Okay, so we'll multiply everything by 2 kilo ohms. That'll make our equation a little bit easier. So that'll be 2VA minus 2VC is equal to VC plus VC. And that will give us 2VA is equal to 4VC. And that'll just be VA is equal to 2VC. That's a nice equation here. Okay, so let's write that down somewhere as well. Okay, so that's our second node. Good. Now we'll deal with our third node. Just a note, you don't need to do an equation for your ground node, of course. You'll see why in a sec. Okay, so for our third equation for node B, this one's a little bit more complicated. So let's try the current lines. So we said that this current here is going this way, so it's going to continue going this way. This current here is going to continue to go this way. So they're both going into node B. This one over here, we can just say it's going out. Okay, this one over here, we can say it's going out. This one over here is 5 milliamps going in. No choice about that. And over here, earlier we just drew an arrow going up, so we'll just keep that arrow going up through this resistor. Okay, so we've got 1, 2, 3, 4 currents going into node B. So let's write out the equation for that. So the sum of the currents going into the node is equal to, first of all, 3 milliamps. So that's 3 milliamps. Oops. I guess this got removed. So that's 3 milliamps. We can also do this one over here. That's 5 milliamps. That's nice. Makes life easy for us. Then over here, we have this one over here. This current, it's going to be so it's going to be node A. So that's VA. So first of all, add VA minus 4 volts minus VB. And remember, it's subtracting the voltage because we're going through the battery the wrong way, right? We're going through the positive terminal to the negative terminal. So we'll get rid of that. And we have to make sure we put all of that over the resistance value. So the resistance here is 1 kilo ohm. Okay. Yeah, that's it. So that's done. That's done. We'll do this one over here, R2. So that one is nice and easy because we're going from node B to ground. So that's just minus 0. And that's going to be over 3 kilo ohms. Then we've got this one over here, which I guess I forgot to label. So this one's also moving out of node B. And it's heading towards ground. So it's the same deal. It's going to be VB minus 0 over 6 kilo ohms. And then I think, so we did this, we did that, we did this. We did this one, and now just this one left. Okay, so the current here is, oh, okay, this was, oh my goodness, okay, sorry, I made a mistake. I was just mixing them all together. Okay, so these are the currents leaving. Let's look at the currents entering node B. So there's this one, node 3 milliamps. There's this one over here, which is a VA minus 4 blah blah blah. Okay, so I got mixed up. So this one over here, this current is accounted for now. We've got the 5 milliamps accounted for, and we need to account for this current also coming in. So this current over here is going from the ground, right? So it's going from the ground and gaining 2 volts. So it's ground plus 2 volts. Then it's going to, it's going to go through this resistor, and it's going to head to node B. So that would be minus node B, VB. So remember, we're calculating the current here, right? The current through this resistor. So what I'm saying is that the voltage drop over this resistor is equal to 0 pumped up to 2, so there's 2 volts here. Then we subtract whatever VB is, right? So let's say, for example, VB was 1. Well, that means that 2 volts minus 1 is equal to 1 volt, and that's 1 volt that dropped across this resistor. So, so this formula here captures that idea without knowing what VB is. So that's, and then we divide it by the resistance of the resistor. So it's 2 kilo ohms, and that gives us the current moving through there. Okay, let's just make sure everything is done correctly. Yeah, so this is plus 2 volts because we're going through the battery the correct way. Yeah, that looks right. Okay, so that's all the currents going into node B. Now let's look at the currents leaving node B. So that would be something like this. So I'm moving these over because we already did them earlier. So this VB minus 0 over 3 kilo ohms is this current over here. Okay, yeah. Okay, so that's that one. This one, the 6 kilo ohms one, is this one over here. And let's see, what else is there? Oops. Okay. So that's leaving, that's leaving. Is that it? 1, 2? Yeah, that looks like that's about right. Okay. So now we got to set these two equal to each other, which is a lot of fun. Or I guess we can simplify a little bit first. Okay, let's simplify the out one first, because it's easier. So it's going to be VB over 3 kilo ohms plus VB over 6 kilo ohms. And we can multiply this one by 2. So multiply top and the bottom by 2. And what we'll get is 2 VB over 6 kilo ohms. And that's going to be VB over 6 kilo ohms. And that's going to equal 3 VB over 6 kilo ohms. And of course, that's just VB over 2, right? Okay, sweet. That resolved itself nicely. So that's VB over 2 kilo ohms, by the way, sorry. 2 kilo ohms. Okay. All right, so that is nice. Let's move that over. Okay, and let's simplify this other one over here too. So 3 milliamps plus 5 milliamps, that's going to be 8 milliamps, of course. That looks, well, okay, we could simplify this a little bit more. although I don't really want to. Okay, let's do it. So what I'm going to do is multiply this top and bottom by 2, so that we have a same denominator over here, and then we'll combine them. So that's 2 kilo ohms. That'll be 2 VA minus 8 volts minus 2 VB, VB plus 2 volts minus 2 minus VB. So that's 8 milliamps plus VA. Is there another VA? Doesn't look like it. That's 2 VA. Yeah, that's 2 VA. So lowercase, uppercase. Probably not good to switch them up the way I'm doing it right now, but yeah. So 3 VB, and that's all over 2 kilo ohms. Okay, so that makes our life a little bit easier. So we'll switch this out for our new simplified equation. Okay. All right. So the current in has to equal the current out. So that means that we have 8 milliamps. Well, actually, I don't need to write this out. I can just copy and paste this. So, okay, so this equation, this the current going in is equal to the current going out. So that's this one. Okay, so now these two are equal to each other. And that just means I can get rid of all this to make us some more space. Okay, so now we should probably simplify this a little bit as well. Okay, so both sides have, they're over 2 kilo ohms, so we can just multiply both sides by 2 kilo ohms, and we'll get rid of the denominators. So we'll have VB is equal to 2 kilo ohms multiplied by 8 milliamps plus 2 VA minus 6 volts minus 3 VB. We can move the VBs, yeah, let's move this VB to the other side. And, well, actually, hold on. Okay, so VB, multiply this, so 2 kilo ohms times 8 milliamps, that's going to be 16 volts, plus 2 VA minus 6 volts minus 3 VB. We'll move the VB to the other side, and we'll move the 16 volts as well. So actually, I'm going to leave the 16 volts here, so it's positive, and I'll move all the other stuff to the other side. So we'll have 4 VB minus 2 VA is equal to 16 volts minus 10, 16 volts minus 6 volts, that's going to equal 10 volts. All right. So hopefully we didn't make any calculation errors here. Because, you know, there's a lot of calculations here. All right. So now we're going to move this. That's our third equation. And so now we're good. We've pretty much got an equation for every node. Another way to know that you're good to go is to check how many unknowns you have in your equations, your set of equations, and check how many equations you have. So we have 3 equations, and we have 3 unknowns, VA, VC, VB. So that's 3 unknowns, right? All equations have 3 unknowns or less, and they're all the same unknowns, VB, VA, and VC. So if you got 3 unknowns and 3 equations, then you're good to go. That means the system of equations can be solved. So the first thing I would do here is I would substitute equation 2 into equation 1. That way you can get rid of the VC that's over here. So you have 4 volts is equal to 5 VA minus 2 VC. So if you rearrange this equation here, you'll get V 2 over VA is equal to VC. So we'll substitute that in, VA over 2. And then minus 2 VB. Now you might be wondering, why didn't I substitute in, wait a second, oh yeah. So why didn't I substitute VA and put a VC in here? Well, the reason why is because then you would have VC here and VB here, but your other equation has VB and VA. And you want to make sure that they, you kind of simplify it so that you get a situation where you have two equations and two unknowns. So if you had put in VC, like VA is equal to, like let's say for example, I did that, 5, then VA turns into 2VC, minus 2VC, minus 2VB, and then I got 10VC minus 2VC minus 2VB. Well, now you have VC here, like this equation has VC's in it and a VB, and this equation has VB and VA. So technically you still have three unknowns in your system of equations. You have VC, VB, and VA in your system of equations. You want to get rid of one of them, right? So that's why I substitute in for the way I did, because you'll see that I'll get rid of VC. So if you don't believe me, just watch. Okay, so let's get rid of all this. This is just kind of an intuitive skill that you'll learn as you get more practice. So anyways, if we substitute in the VC, or sorry, the VA, and we get 5 VA minus VA minus 2. And what we get is 5V is equal to 4VA, oh, I'm sorry, 2VB minus 2VB. Yeah, so that's that. Okay. So we can get rid of these two equations here because we put them together and we create a better equation, which is this one here. Okay, so now what we can do is we can actually add these equations and get rid of one of the variables. So our first equation is 4V is equal to 4VA minus 2VB. Yeah, okay. And the other one is 10 volts is equal to 4VB minus 2VA. So what I would do in this situation is I would multiply the VBs so they equal each other. So I would multiply this equation on the top by 2. So what you end up getting is 8 volts is equal to 8 VA minus 4 VB, and you have 10 volts 4 VB minus 2 VA. Then when you add these equations together, what you end up getting is 18 volts, right? 8 plus 10. It's equal to, you add the VAs together, that's equal to 6 VA, right? 8 plus negative 2. And you add the VBs together, so that's just 0 VB, so it's gone. And now we're finally at the home stretch. So what we're going to do here is we're just going to divide by 6 on both sides, and what we get is 3 volts is equal to VA. Okay, from here on it's quite trivial to figure out what VB is going to be. I think that's, yeah, so you got to find a VA, which is 3 volts. VB, quite trivial. So let's do it anyways, just for the sake of completion. You just need to use one of these equations to find out what VB is going to be. So let's use this one. So 4VB minus 2VA, which happens to be 3 volts, is equal to 10 volts. So it's 4VB minus 6 volts is equal to 10 volts. Then 4VB is equal to 16 volts. And then VB is equal to 4 volts. So that's good. Then the current through R1, let's find out. So R1 is this guy over here. And the current through him is pretty straightforward. So what's happening is you have VA, then you're going through a battery the wrong way. Then you go through this resistor, R1, and then you head to VB, right? So RA, we know, VA, we know is 3 volts. VB, we know is 4 volts. Okay, and we still said that the current is going to be down this way, even though it's going from a low voltage to high voltage, which means that our assumption about which way the current moves is wrong. That's fine. You'll see why in a sec. So, okay, so if you start at 3 volts and you go through this battery the wrong way, you lose 4 volts. So you start off at 3 volts and you lose 4 volts. Now you have negative 1 volts, right? So over here you have negative 1 volts. Then you have to go from negative 1 volts to 4 volts, right? So you have to take the difference between that negative 1 volts minus 4 volts, right? So you find the difference between negative 1, so negative 1 and negative 4, which happens to be negative 5. That doesn't seem right. So you start off with negative 1, and you go to positive 4. Sorry, that's where I made my mistake. So you start off in negative 1 on the number line, right? And you went to 4 volts, which is the voltage of VB, right? So that much voltage change occurred across this resistor as you move through this resistor. So the difference between two numbers is a subtraction, right? So that's going to equal negative 5. So the difference, the voltage difference, let's step back a bit. So you remember the current through a resistor is equal to the voltage drop across that resistor divided by the resistance. Now it's voltage drop, but it's actually technically the voltage difference, right? So the voltage difference from one pole to the other side of the pole will tell you the voltage change, the voltage difference. So the voltage change from one pole to the other is negative 1 minus 4 volts. And then you divide by the resistance, which happens to be 1 kilo ohm. Okay. And then the current is going to be negative 5 milliamps. Okay, so the current is negative 5 milliamps. So the real answer is that the current moving through this resistor, R1, is equal to 5 milliamps. But it's not moving in this direction that we had specified. It's actually going to be moving in the opposite direction, like this. So that's really all there is to it. When teacher asks you for current, moving through a resistor, just make sure you give the absolute value. Absolute, as a reminder, just means the positive value. And they probably won't ask for the direction, but it's good to know just for yourself. All right, well, that's it.